In this set of notes, we're going to learn our first set of basic differentiation rules, which are essentially going to be shortcuts that are going to allow us to calculate derivatives without having to use the limit definition of the derivative every single time. So just to get us into this, we're going to briefly review the limit definition of the derivative. We're going to talk a little bit about some notation, depending on your textbook, depending on the resources you're using, depending even on the application of derivatives in this class. We might see some different notation for a derivative, so I want to briefly talk about that here. And then, of course, the main thing is talking about these initial set of rules that can help us calculate derivatives a lot faster than having to use the limit definition every single time. And then at the end, once we've gone through several examples with these rules, we're going to talk about the idea of a higher order derivative and what that involves. So I like to think of the previous set of notes, the 4.1 notes, as this sort of bridge. It's this bridge between limits, which is what we spent topics 2 and 3 talking about, and pretty much the rest of the course, the idea of the derivative. Now we're going to move to integration, finding an integral of something later in the course, but the main focus of this course is on finding the derivative, differentiating functions. And so in the 4.1 notes, we saw that really important idea. The derivative can be thought of in terms of the slope of the tangent line. So remember this example. We wanted to find this, which remember is the derivative of f at a for f, our function, f of x at x squared, specifically when a equals 4. And the way that we did this in the 4.1 notes is we used the limit definition of the derivative. So we used this expression. There's that similar expression, expression number 2 that we talked about as well. We can find that. But basically, this is how we calculated that derivative. We did our work here, and eventually when we did this, we saw that this thing ended up being 8. And the important thing is that this is equivalent to finding the slope of the tangent line at 4. So this is the same thing as finding the derivative at 4. So the derivative, remember, let me actually go back to the previous set of notes because we wrote it down there. Remember, there's kind of 3 ways to think about this idea of slope, and they're all the same thing. They all mean the same thing for us. When we talk about, there's the same example here on page 6. When we talk about the derivative of a function, we can say it's the derivative of the function, in this case at a certain point, x equals 4, which is equivalent to it being the slope of the line tangent to the function at that point, which is equivalent to it being the instantaneous rate of change of the function at that point. So all 3 of these things are the same thing. They're just kind of slightly different ways of thinking about this idea. Now, as you probably suspect, if we had to use this limit definition every single time we were differentiating something, it would take us quite a while to get through the course, because sometimes using the limit definition can take a little bit of work. So what we're going to talk about are some rules for differentiation, some shortcuts that will allow us to more quickly calculate derivatives. So let's talk about a few things before we do that, then we'll introduce these rules, then we'll do a bunch of examples using them. Now, this is mostly just for reference since we're still talking about derivatives, but we just introduced them in the previous set of notes. So this is basically just copy and paste from the 4.1 notes. I just wanted to put it in here just for reference. So remember, if we have a function defined around some point a, we say that function is differentiable. We can calculate its derivative at a if that limit exists. So this was expression 1 of that limit definition of the derivative from the previous set of notes. And this was expression number 2. They will get you the same thing. Some people prefer one or the other. Sometimes one is easier to use depending on the function, depending on everything, but they will both calculate the derivative of the function at a. Or if you don't have a specific a in mind, if you're just talking about at x, just a variable, it will calculate the function that you can use to compute the derivative at a given point. So this is the limit definition of the derivative, the formal definition of the derivative. And when we start talking about the idea of the derivative in terms of how we understand it and express it today, there was a lot of work involved behind conceptualizing calculus. Calculus was developed pretty much around the world in different places. Different pieces of it came about in different places. There were a lot of mathematicians working in the Middle East. There were a lot of mathematicians working in China, India. There were a lot of mathematicians working in Europe, all around kind of the same time, coming up with this general idea of calculus. So there was a lot of mathematicians involved in this process. But when we talk about like the notation that we tend to use today and how we think about and express the derivative today, we tend to go back to two main people, and this is probably a little bit of bias because we're in the Western world, but we tend to go back to Isaac Newton, which I'm sure everybody's heard of before. Among all his other work with physics and optics, he was also a mathematician. And the unfortunately lesser known Gottfried Leibniz, he was a German polymath. He did a lot of work in philosophy, math. He helped to refine the binary system. He did all sorts of things as well. And calculus, in terms of European discoveries, was basically independently discovered around the same time by these two in the late 17th centuries. And part of the reason I'm bringing this up is because due to their discoveries being independent, they didn't use the same notation for the derivative. And other mathematicians working around the same time and a little bit later also introduced other forms of notation. So basically all I'm saying here is there's several different ways to denote the derivative because a lot of different people were working on it. And so there was a lot of different ways to express it. So nowadays there are several commonly used forms to represent this sort of phrase, the derivative of f of x with respect to x. So differentiating a function with respect to a certain variable. Now the three that we're mainly going to see in this course are these three here. This notation with the dot, this was mainly Newton's notation. We don't really see this much nowadays, but that's where that notation came from. If you ever see an f with a dot over it like that, that's Newton's notation for derivative. These notations were mainly used by Leibniz. We still use these quite frequently today. We'll see these in this set of notes. And this notation, the prime notation, which we kind of focused on in the previous set of notes, that was mainly developed by Lagrange. Other mathematicians used it as well, but these are sort of the main three that we're going to see in terms of notation in this course. And this might seem a little bit trivial to bring up. It's like, okay, it's notation, big deal. But it is important to recognize different notations for the same thing because, like I said, different textbooks, different professors, different resources may use different forms of this notation. Just know it all means the derivative. We're taking the derivative of a function with respect to a certain variable. If we have a specific value of interest, so say at a, so like at x equals 4 or x equals 20, we can see we basically just plug in the a to the prime notation. For the d dx notation or df dx notation, you might see it listed here or plugged in there. Newton's notation, plug it in as well. Just several different ways of denoting this idea and indicating that that's what we want to do to a function. Now, we're going to mainly use Leibniz and Lagrange notation because they're the most commonly used and they're either the easiest to write, the fastest to write, so that f prime of x, nice and fast, easy to write. And once we get into dealing with like higher order differentiation, as we'll see later, related rates if we get to it, optimization, Leibniz notation can be a little bit more intuitive to follow in terms of what we need to do with our differentiation. So I'm going to switch amongst these first three forms in this set of notes just to get us some practice recognizing them and knowing that they all really do mean the same thing. All right, so on page 3 here, this is where we really get into the main first set of rules that we can use. So there's quite a few differentiation formula and rules that we can use as shortcuts for calculating a lot of the derivatives we may be asked to find. Now we're going to learn additional rules later. We're going to talk about the chain rule. We're going to talk about different kind of types of differentiation, tricks to differentiation a little bit later, but these are sort of like the big basic ones. We'll add on to this as we go, but these are the big important ones that you'll use a lot throughout this course, and if you go on to take more calculus, this will form that basis of basically rules that you'll need to know to differentiate. All right, so let's say we have two functions here. Let's say f of x and g of x. They're just functions that can be differentiated, and let's C stand in for our constant as we usually do. Our first rule tells us that if we are taking the derivative of a function times a constant, we can basically take the constant out and differentiate the function and then multiply it by the constant. So the derivative of a function times a constant is a constant times that derivative of the function. The second rule tells us that if we're taking the derivative of a sum or a difference of functions, the derivative is going to be the sum or the difference of the derivatives of the individual functions. And some of these you might recognize, they kind of follow from some of those limit laws that we talked about way back in topic 2. A lot of these are very similar, or at least a couple of these first ones are very similar to those limit laws in terms of breaking things up. Now there's two rules here that are important for differentiation that are maybe a little bit longer, a little bit more involved. They're the product rule and the quotient rule. So the product rule, let's start with that one, is used when we are taking the derivative of one differentiable function times another. So f of x times g of x. The product rule tells us that that's going to be the f of x function times the derivative of the g of x function plus the derivative of the f of x function times the g of x function. Now, since this is addition and since these are multiplication, the order doesn't matter, but it's just f of x times g prime of x plus f prime of x times g of x. You'll probably get enough practice with this that you'll memorize it, but just in case you don't or you can't, it will be on the formula sheets, most likely. So that's an important one. We'll see it a lot. The other important one that we'll see a lot that's a little bit more involved is the quotient rule. And this one is used when we are taking the derivative of some function divided by another. So f of x divided by g of x. So this one's a little bit more involved. And this one, the order does matter because we have a subtraction here. So it's g of x times f prime of x. Notice here in this notation, or in this layout, f of x is the numerator function, so make sure g of x matches with your denominator, f of x matches with your numerator function. So denominator times the derivative of the numerator minus the numerator function times the derivative of the denominator function, all divided by the denominator function squared. And notice we're not taking a derivative there, it's just g of x squared. And as always, assuming that that denominator function is non-zero. Now, my calculus teacher way back when she was teaching us the quotient rule, said a little rhyme, and I still remember it in my head, and I still say it when I'm doing the quotient rule in my head. So if you're somebody who's kind of maybe like an audio learner and like to remember things with like a little song or a little mnemonic, well, it's not quite a mnemonic device, but something to help you, this helps me a lot. So we've got our high function over our low function. So it's low d high, so denominator times the derivative of the numerator, minus high d low, numerator divided by the, or numerator times the derivative of the denominator. Getting my colors mixed up. And then on the denominator we have square the low, and there you go. So low d high minus high d low, square the low, and there you go. That's still in my head, so if that helps you, I put it in there for us. Now, the fifth one here is also very important because a lot of the times, as we'll see, our functions are going to involve something with a power. So x raised to some constant n. We can use the power rule. The power rule tells us if we are taking the derivative of x to the n, specifically where n is a constant, we take the constant or the exponent out front, and then we subtract 1 from the remaining exponent. So it's n times x to the n minus 1. That's the power rule. Now I just have a note here because, again, for some people you've been dealing with exponents and these sort of things recently. For some people it might have been a while. So just a reminder that if you have something raised to the power 1 over n, that's the same thing as taking the nth root of x. So for example, I've got these down here, but I'll write them up here. Another example, if I have x to the, say, 1/3, that's the same thing as taking the third root or the cube root of x. So that's the same thing as the cube root of x. And if you have an x raised to a negative exponent, that's the same thing as taking 1 over x to the positive exponent. So if I have x to the -4, for example, that's the same thing as 1 over x to the 4th, which is the same thing I have here. Just a couple things worth remembering, because sometimes when we rewrite an expression at the end, sometimes people trip over the, oh, how did you get from here to here, or how did you get from here to here? I just wanted to put this note in here to help refresh our memories about some of those weird little things we can do with powers. Now, on the next page, I have a couple formulas for special functions. And these are ones we will start running into more and more. We're going to do more stuff with some of these later, so right now we're basically going to use them just to practice with these differentiation rules. But later we're going to spend a little bit more time dealing with, say, trig functions or the natural log function, things like that. So we'll see a lot of these in practical use later. But since we're learning a bunch of these rules, might as well have them on this page here, even if we're not doing anything special with them yet. So first one here, the derivative of a constant is 0. Now that can be a constant on its own, so maybe f of x equals 4. It could be like f of x equals, I don't know, 8/44. It could be f of x equals, I don't know, 10 plus pi. If there is no variable being multiplied by the constant, the derivative is 0. So a derivative of just a constant on its own is 0, which if you think about, again, what the derivative means, that makes sense. Because, for example, if I were to plot f of x equals 4, 1, 2, 3, 4, that's just this straight horizontal line at 4. And if I think about the derivative or the rate of change of that function, well, my horizontal line has a slope of 0. My rate of change is 0. There is no change to this function because it is a constant. So its derivative, its rate of change, its slope of the tangent line is going to be 0. If we're taking the derivative of e to the x, just the exponential function raised to the x, this one's nice. The derivative is the function itself. Now, like I said, we're going to do more with this later, so if you're like, I don't remember what that function means or what it is, we'll see it later. There's also going to be a little review sheet under the pre-calc folder on D2L talking about this function, kind of reminding us of what it is before we do more stuff with it. Same thing for the natural log function. So if we take the derivative of the natural log of x, it's going to be 1 over x. If you don't remember what that function is, we'll see it later in more detail. You can review it in the pre-calc folder. And everybody's favorite thing, the trig functions. So all of our trig functions have derivatives as well. So the derivative of the sine of x is cosine of x. Derivative of cosine of x is negative sine of x, etc. Remember these negatives. Sometimes it's easy to drop them or forget them for some of those derivatives. Again, we're not going to do too much specifically with trig functions other than use them to practice calculating derivatives right now, but we will see them when we do more stuff with trig and inverse trig functions and applications of functions and derivatives later in the course. So it's all here. A lot of these will be on the formula sheet as well. But like I said, we're probably going to get enough practice doing these that you will have a lot of them memorized. I know I still have to refer to the trig derivatives sometimes because I don't see them very often, but you'll probably commit a lot of these rules to memory even without doing it consciously because we'll do a lot of practice. So speaking of practice, let's look at our first example here. This is the middle of page 4, example 4.2.1, and we want to find the derivative of f of x if f of x is this function here. So we want f prime of x, and I'm going to use, so this is Lagrange notation. I'm going to keep using this just because it's in the problem. So f prime of x is going to be the derivative of this thing. So 5x to the negative 2, it's like we're taking the derivative of that, right? Because it's our function. Now we have a constant here, so if I want, I can take the constant out. Remember, that is one of those rules we talked about up here. That was our first rule. If I have a constant, I can take it out of the differentiation process, put it in front. So I can write this as 5 times the derivative of x to the negative 2. Now this piece is a variable raised to a constant, right? X to the negative 2. So what I'm going to do is I'm going to use my power rule. I'm going to use that last one here on page 3, this one here. So this is going to tell me that I'm going to take that power, even though it's negative, that's fine. I'm going to drop it in front, and I'm going to subtract 1 to get my remaining power here. So there's my 5. I'm going to take this negative 2, I'm going to put it in front, and then I'm going to take x and raise it to negative 2 minus 1. That's my power rule. And I'll just write it here for reference. So what do we have? We have negative 2 times 5, that's negative 10. And then x to the negative 2 minus 1 is x to the negative 3. Now, one thing that always comes up when we start doing this is what format should you leave your answer in? What is an acceptable level of simplification or completion? If you're writing this stuff for your own reference, anything is fine in terms of as long as you've completed all the rules that you need to use. Like, you can leave this as it is. This is perfectly acceptable. That is the derivative of this function. What I would say though is maybe practice simplifying or rewriting some of these a little bit more, just in case if you see them on an exam or you see them on a quiz, you can recognize other forms of this expression. So just to do that here, this is the same thing as negative 10 times, well, this is x to the negative 3, so that's 1 over x cubed. I can write it like that, and then I can also put that negative 10 on top, negative 10 over x cubed. All of these things are fine, they're all equivalent. On an exam, you might see it like in a multiple choice expressed like this. So as long as if you get this answer, you can recognize this as being equivalent, you can convert it to that or write it like that, that's fine. Same thing for work. Most of the work you're going to be doing in this class is not going to be graded in terms of, we're not going to look at your work, we're going to look at your final answer. The exception to that is the written lab tasks, which we'll talk about, or maybe I already have talked about. But in terms of like combining rules or doing stuff kind of all at once, that's up to you. You can break it up like I did here. You can also, maybe once you get faster with this, you can say, oh, I don't really need to make a separate step, taking that constant out, I can kind of do all of this at once and say, oh, I'm going to drop the -2 to the front, multiply it by 5. That's going to be -10 times x to the -2 minus 1. Or you can even just say, oh, -10 times x to the, well, what's 2 minus 1? -3. That's really all up to you in terms of how much work you want to show. When you're doing a written lab task, we are going to maybe ask you to do a couple in between steps. So maybe not jumping directly to this, but showing the use of the power rule or something like that. But for your own work, whatever level of work you want to show that you're comfortable with should be fine. Now for some of these intro ones that we're doing here, I'm going to break it down quite a bit. Later when we start focusing on like the application of this stuff, I'll probably start doing multiple steps at once or skipping an intermediate step. But for now, I'm going to try to write out all of the pieces so that we can see exactly how these rules work. So here was an example of the power rule in action. Let's look at the example here at the top of page 5 and see what we want to do here. So here our function is this, the natural log of x times the cosine of x, and we want to find the derivative. Now, what I always recommend with these functions is if you're just trying to find the derivative like we're doing here, try to recognize the form of your function. Do you have like things added together? Is it a ratio of functions? Is it a multiplication of functions? Do you have a power that you're working with like we did in the previous example? Here, I have a product, right? I have this function of x times this function of x. And so since I want to find the derivative of this product, I'm going to use the product rule, our third one from whatever this page was, page 3. Now notice, again, just for reference, all of these rules, the way I've written them is I've written them with Leibniz notation. So the derivative with respect of this thing is this. I've also kind of combined in a little bit of Lagrange notation. They mean the same thing. So let me just copy this down so we don't have to keep scrolling back and forth. And then we can use this in action. So the derivative with respect to x of f of x times g of x is going to be f of x times g prime of x plus f prime of x times g of x. So that's our product rule from page 3. So let's do this. Let's find this derivative, f prime of x. And like I said, I'm going to write this out in kind of pretty incremental steps just because we're just starting to learn this. We'll start kind of skipping things as we get more familiar. So for those of you who are like, oh my gosh, that's so many steps to show, put this video on 2-speed if you want to, or just skip ahead in the tracking. But for those of you who want to see it broken down bit by bit, let's do that together here. All right, so I'm going to take my first function. Here I've underlined that as the natural log of x. And I'm going to multiply that by the derivative of my second function. So right now, I'm just going to write that as cosine of x, and we're going to take the derivative of that. Plus the derivative of my first function. So the derivative of the natural log of x, notice I'm not taking the derivative here, I'm just denoting that we're going to, times g of x, times my second function, so times the cosine of x. So natural log of x, I'm not taking the derivative of that, so I'm just going to rewrite it here. The derivative of cosine of x is negative sine of x, so don't forget that negative. So this is going to be times negative sine of x, and then plus the derivative of the natural log function, natural log of x, the derivative of that is 1 over x. Times, we're not taking the derivative of cosine of x, so I'm just going to write it as cosine of x. And this is the product rule. And I'm just going to rewrite this one more time to make it look a little bit nicer, make it look prettier, as I always like to say. I'm going to put this negative out front, negative natural log of x times the sine of x. And then I've got this 1 over x and this cosine of x. I'm just going to put those together as a fraction. Cosine of x over x. Again, either one of these is fine, this or this. I'm going to put my box around this because it looks a little nicer. And again, on an exam or on a quiz, you'll probably see this form over this form. So get some practice simplifying or combining terms or combining fractions, that kind of thing. What about this example? F of x equals pi times x plus e to the x. And we want to find this, which is Leibniz notation, the derivative with respect to x of this function. So this is the same thing as f prime of x, just using different notation. So derivative with respect to x of f of x is going to equal, well, what do we have? So my first piece here is pi times x. Pi is just a constant, remember, it's just a number, it's just a constant. So I can actually take that out and multiply that by the derivative of x. And then I'm going to add to that the derivative of e to the x. So I'm using that first rule where I'm just taking that constant, pulling out of the derivative form. And actually, let me be consistent with my notation here. We started with Leibniz notation. Let's keep using it. Again, just to emphasize it's the same thing. So I'm taking the pi out, and I'm taking the derivative with respect to x of x plus the derivative with respect to x of e to the x. So same notation as those apostrophes, or same meaning as those apostrophes, just with different notation. Now, what do we have? So we have pi. This, and I'm going to show you a faster way to think of this in a second, but right now, think about this as x to the 1, right? Technically, this is a power, x to a constant, so I can use the power rule here. I can say this is going to be, I'm going to take that 1 out to the front, 1 times x to the 1 minus 1, and then derivative with respect to x of e to the x, that's one of our special cases, that's just e to the x. So here I'm using the power rule. All right, so I have pi times 1 times x to the 1 minus 1 x to the 0 plus e to the x. Well, anything raised to the 0 is 1. So this is just going to end up being pi times e to the x. Sorry, pi plus e to the x. Now, this is kind of the longhand way of doing this problem. It's correct. It's perfectly fine to do it this way. We use the power rule for this x. We pulled this constant out front. Those are all completely acceptable ways to use the rules that we've talked about, right? But there's kind of a faster way to think of some of these pieces. So these are some things that can kind of help. Let's put here more shortcuts, because these are things you'll probably run into fairly frequently, and if you remember these little shortcuts, these can be a lot faster. If I'm taking the derivative of just plain old x, just x on its own, that derivative is always going to be 1. So the derivative of the variable itself is 1. If I'm taking the derivative of a constant times a variable, just c times x, just a constant times just a plain old x, that's always going to be the constant because the derivative of the x is 1. So it's kind of a faster way. If you always remember, if your function is just f of x equals x, the derivative of just plain old x is always going to be 1. If your function is, say, 44x, the derivative of that is just going to be the constant. Now, of course, you can have other things involved in that, in pieces of that, but this is kind of a set of shortcuts that aren't explicitly mentioned in the previous pages, but they're worth knowing because they make this a lot less work. We don't actually have to use or remember the power rule when we've got like pi times x. Technically, we could use the power rule here and that little rule about pulling the constant out, or we can remember, oh, pi is just a constant. The derivative of this is just pi, which is what we saw for that piece of the problem. Okay, so just a couple additional shortcuts to help shorten the work, simplify things a little bit. Let's do a couple more. Here, we're letting f of x equal the natural log of x plus the square root of x minus 3. Here's some slightly new notation. We want to find, there's Leibniz notation, the derivative of the function with respect to x at a specific value, namely when x equals 2. Now, when I'm doing this process, I like to ignore this. So if I know I need to find the derivative at a certain point, like x equals 2, or x equals 8, or x equals -5, I ignore that until I'm done because I want to make sure I do my derivative process correctly. I don't want to plug this in before I need to, otherwise I might treat it like a constant when it actually isn't. I want to treat x like a variable until I'm done with the differentiation process. So, with that in mind, I'm just going to ignore this for right now, and we're just going to find the derivative with respect to x. So this is going to be the derivative with respect to x of this whole big thing, the natural log of x plus the square root of x minus 3. And actually, let me do this now because it'll make our lives easier. Square root of x. What is that as an x raised to something? Well, square root of x, remember, is the same thing as x to the 1/2, because we talked about this up above. If I have x to the 1 over something, it's the something root of that, right? So x, here's x to the 1/2. That's the square root of x. So if I have the square root of x, I'm going to convert it to x to the 1/2 because that's going to make it maybe a little bit easier for me to use, as we'll see here, the power rule. Now I could break this up with my notation and write the derivative of this plus the derivative of this plus the derivative of this, but I'm just going to do it all at once. I'm going to take the derivative of all three of these pieces all at the same time. So let's start with the natural log of x. We just did this, but let's look at the rule again. The derivative of the natural log of x is just 1 over x. So that first piece is just going to be 1 over x. This piece is x raised to a constant, so I'm going to use the power rule. I'm going to use my fifth rule from page 3, where I drop that power down and subtract 1 from it. So even though it's a fraction, I can still use that rule. That rule applies for any constant, any number. So I've got plus, then I'm going to use my power rule here. I'm going to drop the 1/2 to the front, times x to the 1/2 minus 1. That's the power rule. And then I've got minus 3. What's the derivative of a constant on its own? The derivative of a constant on its own is just 0. So let's simplify this a little bit. Let's rewrite it a bit. I've got 1 over x plus, what's that? 1/2 x to the negative 1/2, right? And then the 0 just goes away. Let's rewrite this piece a little bit. So 1 over x plus, I have 1/2, and then this piece here, x to the negative 1/2, that's square root of x, but it's negative, so it's going to be 1 over x to the 1/2. So I'm just employing the negative here. The negative puts it as 1 over x to the 1/2, and the 1/2 is our square root. So this is 1 over x plus 1/2 times 1 over the square root of x, which I can combine that whole thing in parentheses, 1 over x plus 1 over 2 times the square root of x. So that's my derivative. And again, try to practice with simplifying or rewriting terms like this, because this might be an expression you would see for this derivative on something like a midterm. Just be able to recognize it. Now this isn't the end, right? We don't want this. We want this derivative at x equals 2. So let's finish this by finding the derivative at x equals 2, which just means every place I see an x in this expression, I'm going to replace it with a 2. So that gives me 1/2 plus 1 over 2 times the square root of 2. And that's the answer that I want. Okay, so just a little bit more practice with the rules, just a little bit more practice with simplifying things. Let's do a couple more and then we'll talk about higher order derivatives. So let's go to page 6. So we're told, let me scroll actually back up here, we're told that the derivative of the tangent of x is equal to secant squared of x. And we want to show or demonstrate that that's true in this case. Now, one thing I do want to mention here a little bit about trig notation, the way you might see trig notation. Typically, when you've got a trig function, the exponent is written next to the trig function, but it's equivalent to, say in this case, this is the secant of x, and that whole thing is squared. So think of this exponent as being applied to the whole secant function. It's just convention, we usually put it like in between the function name and the input to the function. Secant squared of x means this. All right, so how are we going to go about this? So we want the derivative of tangent of x. And we only want to use our derivative rules. We're of course told this one, but let's pretend we don't know that. So what's another way that we can do this? Well, another way that we can do this, and this is, I think, recommended whenever you're dealing with trig functions, is if you have a function like the tangent or the cotangent or the secant or things like that, rewrite it in terms of sine and cosine. So this is another thing that's going to be or is in the pre-calc folder if you haven't seen trig in a while. We can actually rewrite the tangent function as a ratio of the sine of x, and I'm going to use a little color here, divided by the cosine of x. That's what tangent of x is. And now what I have for my function is a ratio, right? A ratio of two functions. So what I can use, let me move this over here just because we're going to write something else up here. What I can use for this is my quotient rule, right? F of x over g of x. sine of x over cosine of x, I'm going to use the quotient rule. So let me write down the quotient rule here for us so we can refer to it, and then let's plug in our information. So the derivative with respect to x of, I'll say, f of x over g of x is our our quotient rule is low d high minus high d low, square the low, and there you go. Again, that's in my head forever. Thank you to my calculus teacher. So let me color code this a little bit here. There's my upper, there's my lower, I'll use blue. And so we can use this to calculate our derivative here. Move this down a little bit too. So let's use our quotient rule. So I'm going to take my lower function, cosine of x, times the derivative of my upper function. Derivative of sine of x is cosine of x. So I'll have cosine of x times cosine of x. Actually, let me write this in our middle step here. So I won't take the derivative yet. I'll note that I want to. Then I'm going to subtract my upper function, which is the sine of x, times the derivative of my denominator function, so the derivative with respect to x of cosine of x. And then again, careful with the denominator. We're not taking a derivative. We're just taking our lower function and squaring it. So let's do this. Cosine of x times, I already said this, the derivative of sine of x is cosine of x, minus sine of x times the derivative of cosine of x. Remember, that's one we need to be careful with because it's negative sine of x. So negative sine of x, all divided by cosine squared. So cosine of x times cosine of x is cosine of x squared. I have minus times something that's negative, so that's going to be plus sine of x squared all over cosine of x squared. Now here's something, again, it might depend on your familiarity with trig, because the last time you've seen it, but one thing to remember is we actually have an identity here in the numerator. The identity is the squared cosine plus the squared sine of a function is equal to 1. So I can actually replace that entire numerator with just plain old 1. And I end up getting 1 over cosine of x quantity squared. Another note, 1 over the cosine of x is equal to the secant of x. And if we have squared on the denominator, it just becomes secant squared. So I can actually rewrite this one more time to get the thing we're trying to show. This is secant x squared, or writing it in the more sort of traditional way, secant squared of x, which is what we wanted to show here. So there's the quotient rule, and let me write that on here. Let's do another one that uses the quotient rule just because it's one of the longer ones that we're going to see. So I'm going to just copy that. Let's look at this one here. So let g of x equal 2x minus 1 over f of x. And we want to find g prime of 2, given that f of 2 is 3 and f prime of 2 is 1. So we want to find the derivative at a certain value based on some additional information here. And we actually have just some unknown function here, but we know some stuff about it. So the first thing I'm going to note here is this is a quotient rule application, right? We have a function of x on the numerator, another function of x on the denominator here. So I'm going to use, and I'll bring it down here for reference, our quotient rule, just like we did in the previous example. So we want g prime of x, specifically at 2, but let's just think in terms of g prime of x right now. So using the quotient rule, I'm going to take my denominator function, which is just f of x, times, sorry, oh no, I am using the right color, f of x. It's confusing because I've got it in g of x here and f of x, but my g of x, my denominator function, is just called f of x here. So f of x times the derivative of my numerator function, which is the derivative of 2x minus 1, minus my numerator function, 2x minus 1, times the derivative of my denominator function, all divided by my denominator function squared, so f of x squared. Now I have information about f of x and f prime of x at 2. So I'm actually going to go ahead and start looking at this at 2. So this is going to be f of 2 times, well, what's the derivative of this thing? This is 2x minus 1. I'm not going to plug in my 2 yet. This is just the derivative of 2x minus 1. The derivative of minus 1 is 0. Derivative of 2x is 2. So 2 minus 0 minus, this is just 2x minus 1. And since I'm not taking the derivative, I am going to plug in my 2 there. Times f prime of 2. Notice every place that I'm not taking my, or I'm taking my derivative, I'm not plugging in my 2 yet. We're going to do that later. All over f of x squared. So all over f of 2 squared. Now the reason I'm doing this is because notice what I have up here. I'm told f of 2 is 3. So every place I see f of 2, I'm going to replace it with 3. And f prime of 2 is 1. So every place I see f prime of 2, I'm going to plug in a 1. So f of 2 is 3. 2 minus 0 is 2. Minus 4 minus 1 is 3. F prime of 2 is 1. And I'm dividing all of that by f of 2 squared. F of 2 is 3, so that's going to be 3 squared. Which gives me 6 minus 3 over 9, which is 3/9, or 1/3. So notice we don't have an x in here, and that's because we're taking the derivative at a certain value of x, at 2. So we shouldn't have an x in here because the x has been quote-unquote filled in with the 2. We're not getting a function here because we want the function filled in at 2. We're getting a value basically printed from the function. I have a lot of extra practice problems for this, so if you go into the additional practice and resources folder, there will be a big set of problems just dealing with all of these intro rules just to get you practice with it. We will see these rules a lot. So you will get a lot more practice with it just by being in the course. But if you like having that extra practice to make it maybe a little bit more automatic, that's there for you. So the last thing I want to talk about here is this idea of higher order derivatives. So let's go back to what we talked about in the previous set of notes and the start of this set of notes, which is the idea is the derivative of a function is a measure of instantaneous rate of change, specifically the instantaneous rate of change of the function. So f prime of x measures the instantaneous rate of change of f of x, the original function. We can also go further. What if I want to measure the instantaneous rate of change of this? The instantaneous rate of change of the instantaneous rate of change. So how would I do that? What is the instantaneous rate of change of the slope, or the instantaneous rate of change of the instantaneous rate of change? And this is where the concept of higher order derivatives comes into play. We're going to see actual applications of this later. The reason I'm putting it in this set of notes kind of earlier than we actually use it is because it's basically just doing this whole process with the derivative. So higher order derivatives are just functions of functions, derivatives of derivatives. If we, for example, differentiate the derivative of a function, it's called the second derivative of the original function. And with Lagrange notation, we just put an extra apostrophe there. So f prime prime of x. It's the instantaneous rate of change of f prime of x, which right now is like, why in the world would we ever need that? We'll see that later, mostly in topic 9, when we start talking about like concavity and shapes of functions and things like that. So the instantaneous rate of change of the instantaneous rate of change, which again, right now sounds kind of weird, but we'll see applications of that later. So it's the derivative of the derivative. You'll see that written as, say, f prime prime of x. If you're doing a lot of extra derivatives, so like the third derivative, the fourth derivative, etc., you might see it written in parentheses. With Leibniz notation, you'll see the number of derivatives you need to take as like a superscript. And this process carries on as far as you want it to. So if we wanted the instantaneous rate of change of the second derivative, we can differentiate it and get the third derivative. So the instantaneous rate of change of the instantaneous rate of change of the instantaneous rate of change, which again, right now it's like, why? We'll see uses of that later. But basically, if you want to find the nth derivative of a function, you differentiate the original function n times. So basically a lot of busy work right now in terms of like what we need to do. So let's do a couple examples. You'll see this is actually really easy. It's just using your rules repeatedly. So on page 8, notice what we want here. We want the second derivative of this function f of x equals 3x cubed plus 5x squared plus 6x. And the easiest way to do this is to just find the first derivative and then take the derivative of that, because that will give you your second derivative. So let's do the first. So this is just f prime of x. And this is the first derivative of 3x cubed plus 5x squared plus 6x. So it looks like I'm going to be using the power rule a couple times here, right? I've got this 3x cubed plus 5x squared. And I can also like we talked about, take out those constants if I want to. So this is going to be 3 times the derivative of x cubed. Using the power rule, I'm going to take that 3 out to the front, times x to the 3 minus 1. Then for the 5x squared, I'm going to take the 5 out. I'm going to drop the 2, the power to the front, 2x times 2x to the 2 minus 1. And then we can do the same thing for this, or we can remember that a constant times just plain old x, the derivative of that is just the constant. For now, I'm going to keep using the power rule just because we've already used it twice. 6 times, this is technically x to the 1, so it's like I'm taking the 1 out front times x to the 1 minus 1. This is all the power rule. Here, here, and here. And what we get is 9 times x squared, plus 10 times x, plus 6 times 1 times x to the 0. X to the 0 is 1, so we just have plus 6. And again, the shortcut is remembering 6, a constant times x, its derivative is just the constant, so the derivative of 6 times x is 6. So this is our first derivative. Now, if I want the second derivative, I differentiate the first derivative. Or in other words, f prime prime of x is going to be the derivative of that first derivative, 9x squared plus 10x plus 6. So again, power rule, taking that constant out, 9 times power rule for x squared is 2 times x to the 2 minus 1, plus, take that 10 out front, power rule for plain old x is the power 1 times x to the 1 minus 1. And remember, the derivative of a constant just on its own is 0. So we have 18x plus 10. And that's my second derivative. I'll just write that on there for clarity. Second derivative. Let's do one more. Let's find this for f of x equals 3 times the sine of x plus x squared. So here we have a little 3 in our Leibniz notation. This is saying we want the third derivative. So let's use our notation here. Let's find our first derivative. So this is the derivative with respect to x of 3 times the sine of x plus x squared. So I'm going to take that 3 out. It's just a constant. Derivative of the sine of x is, all the way back up here, cosine of x. So I'm going to have 3 times the derivative of the sine of x, which is cosine of x. Here, notice I'm taking a little bit of shortcut with my steps, plus derivative of x squared using the power rule, 2x to the 2 minus 1, which gives us 3 times the cosine of x plus 2x. So this is my first derivative. Second derivative of my function is the derivative of the first derivative. So the derivative with respect to x of 3 times the cosine of x plus 2x. So derivative of my first derivative, which is going to be 3 times the derivative of cosine of x. What's the derivative of cosine of x? That's that one we need to be careful about. That's negative sine of x. So I'm going to have 3 times the negative sine of x plus, and again here I can either use the power rule or I can remember constant times x. The derivative of a constant times just plain old x is going to be the constant, so this is just going to be plus 2. So rewriting that, making it a little bit prettier, negative 3 times the sine of x plus 2. That's my second derivative. Now one more to get my third. The third derivative of my function is going to be the derivative of my second derivative. So derivative of negative 3 times the sine of x plus 2. So now we have our constants negative 3, don't forget the negative. Derivative of sine is cosine, so negative 3 times the cosine of x. Derivative of a constant on its own is 0. So my third derivative is actually quite simple. It's negative 3 times the cosine of x. So that's my desired third derivative. And like I said, we're not going to be doing too much with this stuff until we get to, basically until we get to curve sketching and intervals of increase, decrease, concavity, all of that stuff around topic 8, topic 9. So I wanted to put this here, like I said, because it is just practice using the derivative rules, but I will do a little recall once we get all the way down to topic 9 about what higher order derivatives are and how we calculate them. But for now, it was just some extra practice using our derivative rules.